Hi everyone, Assalamualaikum and good evening. Welcome back to the channel. Today we are diving into our individual circuit analysis assignment. We have two main tasks here. First, we will perform a complete series parallel DC network analysis, and second, we will calculate and find the exact balance point of the Wheatstone's bridge circuit. We are going to calculate the theoretical values by hand and see how they verify inside Tinkercad and look at the final comparison data. And let's get right into the circuit one. Okay. For the circuit one, what we have here is a 9-volt battery, 330 ohm for R1 or RA, and RB is 1000 ohm, RC is 330 ohm, and RD is 100 ohm. Okay, for circuit 1, we need to find the currents IA, IB, and IC, and the voltage drop VA and VB. And what we need to do this manually is we start from the far right branch and collapse to the network back toward the source. Okay, for the step 1, resistor C and resistor D are the single path, meaning they are in the series and we simply add them together. Okay, so RCD is equal to R series lah. Okay, RC plus RD is equal to 330 ohm plus 100 ohm is equals to 430 ohm. Step 2, this equivalence of 430 ohm branch is parallel with our central 1000 ohm resistor, which is RB, and let's find their combined parallel resistance, which is RP. Okay, so RP is equal to RB multiplied by R series divided by RB plus R series. Okay, so the value is 1000 ohm multiplied by 430 ohm divided by 1000 ohm plus 430 ohm. So we got the answer is 300.7 ohm. Step 3. Now we this whole block is in series with our front resistor RA. Therefore, the total equivalent resistance RT is presented to 9-volt battery is RA plus R parallel. Okay, which is equals to the value, the RA is 330 ohm, RP is 300.7 ohm, and we got the answer 630 ohm as 0.7 ohm, 630.7 ohm. Okay, and now we are solving the for current, current and voltage. Okay, with our total resistance locked in, we can use Ohm's laws to extract our target parameters. So step 1, we need to find the IA first. Okay, total source current. Okay, total source current is V series divided by RT, which the value is 9 volt divided by 630.7 ohm is equals to 14.27 milliampere. Okay, and voltage drop across RA is VA. Okay, VA is equals to IA multiplied by RA. Okay, so IA is the value of 14.27 milliampere and 330 ohm for resistance. Okay, we got the answer is 4.71 volt. And the VB is voltage across parallel node. Okay, which means a V series is subtracts by a volt VA is equals to the value of 9 volt subtract 4.71 volt, which we got the answer is 4.29 volt. Okay, branch current is IB. IB, we got the value of the volt 4.29 volt is divided by resistor B 1000 ohm, which we got the answer is 4.29 milliampere, and branch current IC is VB divided by R series. Okay, so R series and VB, the value of VB is 4.29 volt divided by 430 ohm for R series, and we got the answer is 9.98 milliampere. Now let's check out our live Tinkercad simulation. Okay, wait for a moment. Okay, as you can see here, I've done the simulation at first, but I don't want to do it the second time because I need to understand it first as well. Okay, as you can see here, our meters are hooked up perfectly in line for a current and across the nodes or for voltage. And when we hit run, start the simulation, our main ammeter register is 14.2 milliampere. Voltmeter A is read as 4.7 volt, and voltmeter B shows the 4.28 volt. Okay, and the value is spot on as well as the calculation, which is the differences between them is 0.01 values. Okay, so that's all for circuit 1, and next we are going to the circuit 2, Wheatstone bridge balance. Okay, now let's move on to the part 2 of our assignment, where we analyze Wheatstone bridge circuit. Our main objective here is to understand the relationship between the bridge parameters and find the exact balance point where the circuit achieves complete equilibrium, meaning the current through our central meter drops to absolute zero. Okay, first let's establish our known values given by the assignment sheet, which is, you can see there, our DC power supply is set to 9 volt, and the fixed resistor on the bridge branches are R2 equals to 150 ohm, R3 39 kilo ohm, which is 39,000 ohm, and R4 is equal to 330 ohm. We are using a potentiometer for our port, which is operate on a knob scale from 0 to 10. Crucially, the sensitivity factor of this potentiometer is a 2.5 kilo ohm per unit scale. This means at full scale 10, the maximum resistance is 25 kilo ohm. Okay. Next, to find our target the values mathematically, we use the fundamental Wheatstone bridge equilibrium ratio. For a bridge to be perfectly balanced, the cross multiplied resistor arms must satisfy the following relations. Okay, let's get to know to the calculation. For a bridge to be perfectly balanced, the cross multiplied resistor arms must satisfy the following relation, which is R port divided by R2 equals to R3 divided by R4. So the meaning is R port is equals to R2 multiplied by R3 divided by R4, and R port for R2, which is 150, R3 39,000 ohm, and R4 is 330 ohm. Okay, the answer for R port is 70.73 kilo ohm, and the knob scale position and Now that we know the exact resistance needed for equilibrium, we can figure out where to physically set our dial knob by dividing this value by our scale sensitivity, which is knob scale position is equals to 17.73 kilo ohm divided by 2.5 kilo ohm per unit, and we got the answer is 7.09. So as requested by the assignment, we sweep our potentiometer scale 1 all the way to scale 10 to map out the circuit's characteristic. When plotting these readings, two highly notable behavior emerge. We conclude that we got the bridge voltage versus resistance curve start in positive territory, uh, positive 0.434 volt at the scale 1, slopes smoothly downward in a non-linear decay, and cross the horizontal zero line at our target point. And the bridge current versus resistance curve follows an identical trend, dropping from positive 0.926 milliampere until it intersects the horizontal axis at the exactly 0.0 milliampere. By identifying the x-intercepts where these curve hits absolute zero on our graph, we visually confirm our balanced resistance state of 17.73 kilo ohm. And okay, so let's take a look at our live verification inside our Tinkercad. Okay, from this, as you can see, our bridge component are laid out cleanly, and we have positioned the potentiometer knob just past the 7 mark on the dial, and matching our calculated scale value of 7.9, supposed to be 7.09, but in the Tinkercad we got 7.05. Looking closely at our center measurement indicator meter, it registers exactly 0.00 ampere. This provides undeniable proof that our manual calculations and our simulated bridge model are in perfectly alignment. Okay, so to wrap things up, let's take a look at our final evaluation matrix, which is calculated resistance 17.73 kilo ohm versus simulation resistance 17.73 kilo ohm, supposed to be, but we cannot see in here, I think. Yeah. Okay, and calculated knob position, I got 7.09 versus simulation position, which is 7.05. At the target balance current 0.00 milliampere versus simulation, which is I got the same as well, 0.00 ampere. The verification is complete success, and our circuit behave exact as circuits theory predicts. Thank you all for watching, and I will see you in the next analysis lab. Bye.